Okay.
So
Thank you very much. So also, Sergey, I'm sorry. So if you ask some questions, maybe you better come nearer because it's also
hard to
not easy
hear.
to hear when you stand far away. It's I'm afraid not always easy to hear. Okay, so let me then share some slides. Just a moment.
Yeah, so Sasha had some ideas that he'll share with us.
Okay, just a moment. Do you see my screen? No?
We do,
Not
yes.
yet? Yes.
Yeah.
But just a moment. So do you see my presentation now?
Yes, yes.
Okay. Thank you very much. Just a moment. Okay. So first of all, thank you very much for inviting me, for Michael and for Sergey. Thanks a lot for your interest. So I'll talk about the pathfinding on the Cayley graphs. So let me first remind the problem. So assume we have some group and we have chosen some generators. And there is an element. The task is quite simple. We want to represent given element as a product of the generators. This task have an equivalent formulation that given some node on the Cayley graph, we need to find a path connecting this node to identity. Why this formulation is equivalent? So first, let me remind what is a Cayley graph. It is very simple. Nodes of the Cayley graph are just the elements of the group, and two nodes are connected by the edge if there is a generator, such that you multiply one element by the generator and you get another element, U and V. And so they are connected if such generator exists. So on the Cayley graph, each edge is a generator, and hence any path is a sequence of generators. And by our definition, the product of the elements in the sequence gives an element which corresponds to node which is obtained by the starting node by the multiplication of these elements. So essentially, any path you can think as some element, and the concatenation of the path essentially the product of the elements. So example and some restrictions for the setup, what we are doing. So part of the ideas which we describe below can be applied to some general groups, but we are now restricted to the case of the permutation groups and matrix groups. So for example, let us consider the Rubik's group. That means the generators are given just by the permutation, explicitly given. For the Rubik cube, for example, there is some well-known families of the generators which correspond to rotations of these slices. And if slices are parallel to each other, obviously the generators will commute. So essentially in the Rubik group, we have three family of the commuting generators. And each generator has order 4 in this family. But the group itself, of course, is quite huge and non-commutative. So what we want to do? So we want to develop a kind of library which will be compete with the gap. This is a mathematical computer algebra software, and we want to overcome the gap. This is the slogan. So we want to do better. So as a user interface, user input some explicit permutations as the generators of the group or matrices. So, oops, sorry. So for example, here user input the permutations like this: F0, F1, just explicitly given permutations. And another permutation W. And the output of our system that should be the sequence of the generators such the product gives an element as a product. So how we estimate good or bad our system is working? So of course the path should be the shorter the better. The faster system is working, the better, and the larger group is supported, the better. So basically, these are the three main criteria. So currently, we can support the group of order 10 power 40. This is, for example, cube 4x4. And we are achieving it for training time is about 40 minutes now, and solution time is about 3 minutes. And the length is about 70. So optimal is around 40. So we are quite far from optimal now with these parameters, but we are improving. And computer algebra system GAP cannot do such large groups. Hopefully next week, we will improve the speed to something like several minutes. I think this is quite possible. Another example for the Rubik's Cube standard 3x3, we almost can approach the optimal length and beating the previous deep learning system like DeepCube and AlphaCube. And gap is very far from the optimal length. It gives length about 100, while optimal length about 20, but gap is very fast. So it can do it in 1 second, something like that. So we can do something like in 1 minute, the same. But we will provide much better length. So these are kind of what we hope to do. And partially this is achieved. So what our approach is, and I think it's interesting for Sergey maybe, that it's a little bit alternative to reinforcement learning. So reinforcement learning approach for us is optional. We can do it, or currently we are working without it. But hopefully we'll support in the next version. So the approach is quite simple. So we create the train set just by random walks, starting at, for example, at the identity element. And so we create lots of pairs. G is just element of the group, so a permutation, for example, in our case. And K, this is the integer number. How many steps of the random walk we need to achieve this element. So in some sense, random walks, it's like AlphaGo is playing with itself. So here, there is no game. So instead of playing with itself, we just do random walks on the graph. But in some sense, this is the same idea. This is a remark. So our train set is element and number of steps it was achieved by the random walk. So in the next step, we are training the machine learning model to predict this integer number k from the permutation G.
So you predict, can you hear me, Sasha?
Yes, yes, please.
You're trying to predict just k or the entire path?
For the moment, we are trying to predict just k.
Just k, okay.
But we can also, this is possible approach, but we even thought about this and we have some notebook, but so if you think about producing the path, the task will be very similar to language translation, because you have a sequence of numbers which represent the permutation elements G. G is a permutation. So for example, 2, 3, 1, 10. So it's a sequence. Mm-hmm. And if you want to produce the path, it will be another sequence. So it will be a standard task, sequence to sequence. Yes.
Right.
So we even have a notebook, but we didn't pursue this way, kind of. So for the moment, we pursue more simple way, but that's a very interesting direction to follow.
Well, this is a simpler function to learn, and if you have a good approximation to it, you can get the path as you're about to explain.
Yes, exactly. So in a sense, it's enough to predict K, but on the other hand, it's interesting to explore this option. So the analogy with the translation task, it's like from one language to another, like sequence to sequence. I think it's very interesting, but for the moment, we do not follow it. So we're just trying to predict this integer number K, just the how many steps we have passed. So input is the permutation, and the output is just prediction for the K, yes? Okay, now the almost final step for us is to use this prediction to actually find the path. The idea is very, very simple. So you start from some element, for example, V, and you compute the predictions of the machine learning model for all the neighbors. And just you choose the neighbor which is predicted to be closer to the destination, to the identity. And you make a move to this node. And then you repeat. And so on and so forth. Finally, you hope you will find the destination. However, of course, if our model is perfect, so exactly given us this K, then this approach will work and give us the shortest possible path, and it will give us with minimal resources. So it will be shortest path and given in the shortest possible way. Unfortunately, we should not hope for the model to be that much perfect. Because, for example, if you think about AlphaGo, they have the model, but it's not enough to predict the move. They also use the Monte Carlo tree search. So AlphaGo is a combination of the two algorithms. Only neural network is not enough. And so for us, it's the same. Only neural network, still, at least for the moment, we are unable to train this such perfect neural network which will be able to find the solution. So if we'll do like this with the neural network, the main problem will be local minimums. And this will mean that we'll cycle. So if we are in the local minimum, we go to the neighbor, but then we go back to the local minima. And so this is infinite cycle.
Does that happen in practice?
Sorry, Michael.
Does that happen in practice, that you get local minima?
Yes, surely. So that's the main problem. You see local minimums just almost everywhere.
Yeah, your algorithm works. I thought your algorithm works. It doesn't work in this form, or it does work in this form?
Sorry. So what I have described is a simple so-called greedy algorithm.
Right.
And now to make it work, we should modify it. We should use either, for example, A star or Metropolis or beam search or some other algorithm. So currently we use beam search, and it works.
Okay, so it wouldn't work if it were just following the obvious line of gradient descent. Do you have any sense of how many local minima the thing has, in any sense, this function?
Oh, that's a very good question, but we have not analyzed it very carefully. But impression is it's like everywhere. So I mean, whatever you go, you will see something like local minimums are everywhere. But
Okay,
maybe I'm not correct. But just kind of with the greedy algorithm just nothing works.
Okay.
We need a beam search, for example, or A star or something like that. Just to give you some numbers, so to achieve the almost optimal length for the cubic 3 by 3, we are using the beam width about 1 million. It's quite large. That means, so let me, remind you the idea of beam search. Well, maybe everybody knows, just tell me.
No, no, say it, because it could mean different things here. Yeah, remind us.
Okay, yeah, sure. So the idea again is very, very simple. So you start from one node, for example, V, and we fix the main parameter is something like beam width, which can be, for example, 1 million or 1,000. So as a first step, let us make just, for example, many copies of this node. For example, 1,000 copies. So this is technical. Then, so we will compute neighbors for all these 1,000 nodes. Then we compute machine learning prediction for all these newly obtained nodes. But then we choose only top 1,000 nodes which are closer to the destination according to neural network prediction. So let me repeat it again. For example, for Rubik cube 3 by 3, you have something like 12 moves, depending on generators. Imagine that beam width is 1,000. So we produce 12,000 new nodes because for each of the 1,000 we compute 12 neighbors. So we get 12,000. For each of these 12,000, we compute the neural network predictions. We are sorting them in the ascending order and choosing the top 1,000 most close to the destination. That means that the predictions of the neural network are as minimal as possible. This is the inductive step. So we get 1,000, and then we repeat. For this 1,000, we compute again 12 numbers for each. Again, machine learning model gives prediction. Again, we choose top 1,000 nodes, and so on and so forth.
So the thing you keep track of and that you have a multiplicity in the beam searches the nodes, it's not the whole path. You say, I have like 1,000 nodes moving out, and every time they take a step, I keep the best 1,000. Not
Yes.
forgetting how long the paths were that it took to get there. Just to be clear.
Yes. So this is the simple beam search. We forget the history.
Yeah. Okay. Yeah.
Yeah. And so this is the simplest beam search. Yes, the idea, and it works in our cases for Rubik's cube 3 by 3 and 4 by 4. Works quite perfectly.
So your local minima are shallow. It doesn't take that many paths out or that many steps out to get out of the local minimum.
Yes. So essentially, my intuition is local minima. So it has some size. Yes. If you choose,
clearly there's a depth. There's the minimum direct altitude or difference you would have to reach to get out. So
so if our beam is larger than this depth of the minimum, it just cannot be fixed in the minimum because it's kind of smaller.
Yeah. I mean, if the dimension's not too high, that'll work.
Yes.
Do you try to fix that distance? I mean, once you find a local minimum, of course, that says there's something wrong with your distance function. Do you try to fix it in some way or improve it?
We just we have some interesting observations that sometimes but I cannot be precise. Yes, it's some preliminary observations. I'm not
Okay.
sure.
Because of course you could try to, change, improve the network to get rid of the local minimum.
Yeah, it seems that some local minimums are quite specific. It means they, for example, they look very similar to your destination node. For example, only just this is an integer vector, but maybe only few numbers are different from your true destination. And the machine learning model thinks, okay, it's similar, so I can give a prediction like 0. Yes, so it gives you just you are in the destination, but this is not correct. Yes, but I'm not sure that all the local minimums are this. So for some,
it's hard to know theoretically, but again, you could make a slightly more complicated algorithm that tries to introduce more training examples in these cases to fix that.
Yes, exactly. A couple of kind of theoretical remarks from our experience. So what are the alternatives? Beam search is one alternative. Another, for example, widely used is A-star algorithm. It was used in the previous paper, DeepCube. So what's good about the A-star? It can give you some theoretical guarantees that you will find the shortest path if your heuristics, if the model prediction satisfies some properties, like it's a kind of distance, triangle inequality, and so on. But these theoretical guarantees are not true in the practical examples. So neural network will not give you such a good prediction. And the main problem with A-star algorithm, it's not easy to parallelize it. So for example, in DeepCube, they have written it in C++ code. So everything is in Python, but this part was written in C++. And that's not kind of easy to support, not easy to change, and so on. But the beam search is very simple to write in the Python with the kind of just torch operations, basic torch operations. It will work for CPU, GPU, and just the code is very simple. That's, I think, the main advantage of the beam search, that you will write the code in a very simple way, and you have a very clear parameter, beam width, which controls you kind of the quality. Another thing, we have tried Metropolis algorithm, but it was not successful. So when we changed, first we tried Metropolis, then we changed to beam search, and wow, it works. For Metropolis, it didn't work. Okay, so.
Do you understand why?
Well, Metropolis is something more subtle. So the main point of Metropolis is to produce the distribution which will correspond to the sample from the distribution. So that means it gives you much more information, but we only need to find the local minimum, global minimum here. We do not care about this sampling from the distribution. So maybe Metropolis will kind of too complicated for this task. We have a more simple task. So Metropolis makes random steps, but beam search is making not a random step. It chooses the steps which are closer to the destination, while Metropolis is making the random step, and then you approve it or not approve it. No, I mean, it's not a very careful analysis, but or maybe we just did not tune the parameters of Metropolis, because you have a temperature in it. But we tried to tune, so, and didn't get the result.
Mm-hmm.
Okay, one more remark about the reinforcement learning approach. So for us, this is an optional step. We can use it. So currently we do not use it. So we are developing it, but not using in the main version for the moment, because we have some difficulties. So what is the idea of the reinforcement learning? The main idea of the reinforcement learning is that it can produce solutions for the Bellman equation, but the metric on the graph, the distance to the identity, precisely satisfies the very simple form of the Bellman equation. So if we run the reinforcement learning algorithm, we should get the distance to the identity, exactly what we want to get. If we get it perfectly without any mistake, then again, greedy algorithm will give us the perfect solution, optimal length, and in the optimal way. So our hope is that first we run our algorithm and then we improve it by the reinforcement learning approach. But at the moment, it doesn't work for us. But it's maybe just technical that we have not spent much resources on that approach. Any questions on this? Okay.
There's another thing you could do, which, I mean, this is a comment that Drew made on the Zulip, that you can make algorithms that search in both directions, you know, from the starting point and from the ending point. You know, since you know the whole graph, and try to get them to meet in the middle. And of course, since it's a group, you only have one distance function to learn. You can make any point, you know, be the base point by just, you know, acting with the group. So did you try that?
Not yet. I have thought about it, but I don't see some clear way that it will kind of motivation that it will give.
Oh, it's much better because you only need to find half as long a path. You know, if there's any kind of a search aspect, you know, then you know the search grows, you know, typically exponentially in the length. You know, and that's the for a large group, that's eventually going to be the problem. And now you can, you know, search out in both directions and find two paths of half the length.
Okay, I think I need to think on this, but maybe we can
Also,
discuss.
I don't know if it's incorporated in the problem, or maybe that's what Mike is asking, because if we talk about distance function between two general points on the graph, there is obviously also equivariance with respect to group.
Yeah, exactly. Since it's a group,
it's a highly constrained problem.
Well, he's only learning, I think, the distance to the origin.
Right.
But of course, that gives you the general distance.
Yeah. Once we start talking about 2 points, generic points, then equivariant versions of networks probably would.
Well, no, you don't need it. You can just take the same function. You just compute D of G inverse, you know, G1 inverse G2.
But I think we want to implement maybe somehow almost hard code in a network that it should be equivariant, right?
Yeah, I mean, it's true. You could if you have a particular representation and you know that there's some, you know, I mean, you certainly know that the distance is a conjugation, is the only function of the conjugacy class. So you could certainly use that in defining your network. That would be another possible, you know, direction of improvement. It's right. Did you try? Have you tried more? We talked a couple of weeks ago about SL2Z, you know, discrete infinite groups and subgroups of SL2Z. Have you had a chance to try any of that, or?
No, I haven't tried. So it's possible. So first we want to finish with the permutation setup, and then we will try the metric groups. About the equivariance, so in my mind, so it's possible to make a neural network which will take two nodes and reduce the distance between them. And it should be equivariant with respect to the group. But in my mind, I am simplifying the problem since I have chosen the identity and I am looking for the distance from identity. I have broken this equivariance, but I simplified because now I need only compute distance from one element.
Yeah, that's what you should do, because even if you wanted the distance between G1 and G2, that's the same as the distance
Yes,
from
yes.
G1 inverse G to the identity. So there's no point in learning a more complicated function, but the function has more symmetry. So for example, the distance from the identity to G is the same as to any conjugate of G.
That I'm not sure, because we have chosen the generators. So generators are breaking
But your representation, that's right, the path, okay, you say the path, the distance on the graph is not.
Yeah,
It's not necessarily conjugation, right? That's true, yeah.
Yes. So there should be some symmetry, but they should be related to the generator's choice. So it's, I think.
Right.
Okay. So how much time do I have?
How much time do you need?
Well, I can talk for hours, but I mean, it's.
Well,
10 more minutes.
yeah, maybe.
Okay, maybe
10 more minutes?
Yeah.
10 more minutes. Okay, great. Okay. So Sergey made a great talk for me and my colleagues. And so he emphasized that there are cases where we need to find something like 10 power 10,000 length of the path. That's completely incredible. So my idea that maybe we should think about approaching this problem with the help of the embeddings and so we know algebraic geometry is the queen of mathematics. Yes, so it's solving the algebra and the arithmetic questions by geometric methods, and this is very successful, from Grothendieck, Italica homology, so on. So in a sense, the embedding technique, which is very popular now in machine learning, in language models and so on, and in particular for graphs. So it takes a graph, and for each node, it produces a point in some manifold, typically just in Rn, in Euclidean space. And we hope that embeddings are good, in a sense they represent the geometry of the graph. Yes? But now, the main idea is that we should kind of think in the direction that since we have an embeddings, we can substitute the difficult combinatorial search problems and methods like beam search or star by something more gradient descent methods. Because if we have embeddings, essentially we can, for example, recalculate our distant functions in terms of the embeddings. So it will be defined on the embedding space. And then we can compute the gradient according to the distance functions, which we need to minimize with respect to the coordinates in the embedding space. And then instead of the beam search or A star or whatever, we can go according to the gradient. And hopefully it will be much faster and allow us to kind of make to tackle the problems with a big number of moves. I'm not sure about this size, but I think at least it should give us some improvement according to, comparing to the beam search or so on. But this is the kind of next idea. We are now hope to finish with the current beam search approach, and then we'll think in this direction. But I think this is kind of interesting direction. Okay, so
it depends how many generators you have, because if there's few generators, it's probably faster just to do what you're doing now. But if there are many, then this could be faster.
But yeah, I think yes, you're surely right that many generators will be very good application. But I think that even with the several generators, if we have the gradient, we can kind of move in this direction for many steps. So we can make not a.
Well, you need to convert the gradient into some discrete path. How do you do it?
We can project. So we can first make a step in the gradient direction, and then like it's usually in an LLM, we just find the point which is closest to our gradient point. So you make a step in the gradient direction.
Yeah, it's well defined. I'm just skeptical that it's faster than just doing it for the generators if there's few generators. But it's worth trying.
Yeah, but imagine just the geometric situation that if our graph is a kind of set of the points on the sphere, for example, yes, randomly, uniformly distributed. Imagine just, and so.
Yeah, but imagine the computation. You know, you evaluate it for 6 neighbors versus do this big computation you just said.
But you can make a huge step. You can make in one step maybe 600.
Well, maybe you can make a huge step if it's like the power of a generator, but your steps have to be actual, paths in the group. I mean, maybe you can break it down.
You just make a step and then we'll project it back to the group. And then again, make a step.
Maybe there's some way of taking a big step and converting it into a word. I mean, some combination, not just single step at a time, but maybe. Yeah, that's interesting.
Yeah. Okay. Thank you. Oops. Sorry.
If you had a not slide back there, or
yeah. Yeah, I want to show you a little bit just some slides. So this slide, I think this is something like interesting and maybe useful for the understanding for what we are doing. So at the beginning, I said you a very simple thing that we run a random walk and our target is just the number of the steps random walk have done. Yes. So for each element, we have calculated the number of steps the random walk have achieved. Yes. So very simple, very naive definition. But now I want to make there are some subtleties I want to emphasize for you. So actually, this definition can be rephrased mathematically as a kind of diffusion distance on the graph. But the main point is it will depend on the length of the random walk. So what we are actually computing is in our train set, this number of steps on random walk, we have a key parameter. We always consider the random walks starting from identity, but making, for example, 100 steps or making 20 steps. This is a parameter in our scheme. And things, our train set depends how we choose it. Naive choice of this number of steps for the random walk is something like near to the diameter of the group. Yes, maybe a little bit larger, because you want to cover all the group. So if you choose number of steps for the random walk less than diameter, there will be clearly some points which you do not achieve. It's not good. So you want to have it something like diameter, but random walk is not going forward and forward. Sometimes it makes a step back. And so that's why you want to make this a little bit larger than diameter to compensate that random walk is going sometimes in the back direction. So, but now we can actually compare and compute this diffusion distance for different lengths of the random walk. So here is an example of the small group. It's just Rubik cube 2 by 2, only 3 million elements. So here we can compute the true distance by brute force. And now we can compare the true distance on the x-axis with the diffusion distance on y-axis. And we compare it for different values of the random walk length. And so you see how things are changing with respect to the choice of the length of the random walk which we consider. So if we choose it quite small, near the diameter, so 20, it's more or less goes as true distance. But if we take it quite larger, we have such a sharp growth somewhere at the middle. So at the moment, we do not fully understand this choice of the optimal length of the random walk, and actually we do not fully understand this diffusion distance, and there is no much literature on them. And
I think that's a much studied thing, random walks and harmonic functions on regular graphs. I mean, you have to put another consideration, which is that from the graph you're showing us, the smallest Kmax is the best, but then that will much more concentrate around the identity, right? It starts to become much less likely that you go out distance 20. And so you need to know the density as a function of the distance too. So that's the disadvantage of the small Kmax, is that the density it's always peaked around 0, but then the bigger the Kmax, the more the density spreads out. So if you want to sample the whole group, you have to balance those two factors.
Yes.
Actually, but another question or slash comment, I'm not sure if it's a question or comment, but some literature on this diffusion distance, I think, assumes that graph is explicitly presented. And we're working with non-explicitly presented graphs. I'm not sure if that's an obstacle or not.
By explicitly presented, you mean?
Given, so it's basically machine has access to all information about it, whereas here we're exploring it.
No, he's assuming he knows the group. I mean, there'll be two versions of the problem, but generally he's assuming that we know the group. And we both know the group, and we have some second representation of the group, like a matrix or something, which is just, yeah, that's right. So you're right in general, but.
Yeah, but may I make a just small remark? So we say the diffusion distance, but actually we are not sure this is a distance. We are not sure it is symmetric, and we are not sure it satisfies the triangle inequality. And I haven't listened to the literature.
It doesn't, but it's a much studied thing, the Green's function.
Why do you think it doesn't? I think for Cayley graphs, it should be symmetric. And
yeah, no, it's really symmetric. No, I don't think it literally satisfies the triangle inequality, but I think I know under some conditions, I think you're right that it does monotonically depend on the true distance.
It might.
The basic approximation to it, which is simplistic, is e to the minus d squared over k, times the 1 over k to the d over 2, like in flat space. Right? I mean, that's a first guess you could make for how it's going to behave.
Yes, but it's a flat space.
I know. It's not. But if you want some intuition, that's not a bad intuition. And then you can put in the curvature. So like your finite, your groups are all things analogous to positive curvature.
Yes, you are right. But I see that there can be some subtleties because on the discrete groups there are such elements called the dead ends. That elements, if you come there, you cannot go further. All the neighbors are closer to identity.
Well, yeah, like a sphere too. I mean that's generic and finite.
No, for the sphere you have only one such point. It's on the diameter.
Right.
But in the discrete groups, these elements can be not on the diameter. They're much closer.
Oh, yeah, that's right. And if it were a topologically more complicated manifold, there could be more of them too. I mean, definitely, that's right. I'm not saying the flat space guy is a good approximation. I'm just saying as a first source of intuition, it's you can think in those terms. But I think there are it is a much studied thing, what you're asking.
Well, I have searched for the literature, so I haven't found this precisely. So, Michael, if you can send me something, because what I have found, there is some famous paper called Diffusion Maps. It's in the machine learning community, but they're studying things from
yeah, no,
different angle.
I don't think that's gonna. I mean, I think I'll take a look. Maybe I can find something for you. Yeah.
Okay, so I think it might satisfy the triangle inequality. Why not?
Well, does e to the minus d squared satisfy the triangle inequality?
Are you all right? No, okay. Okay, okay, but okay, but it's not when we look on the plot, it's not so far from the kind of true distance. So maybe it can be just so it might be just okay. Depend on the geometry. So this geometry for the random groups is not like flat geometry. Yes, it's more like a negative curvature.
It's well for your groups, it's like positive curvature. I mean, positive curvature is when geodesics and can converge, and in your groups, like the Rubik's cube, things are going to converge. You're going to get things that wouldn't have been equal in flat space because of the relations they're equal. Whereas like SL2Z, like a tree, would be negative curvature.
No, but these random groups like a Rubik cube or another random groups, we should think as a negative curvature because they're exponentially growing. If you compute the number of elements, you'll see the exponential growth.
Yeah, maybe there's both. Maybe there's, I mean, you don't have to have both be purely negative or positive. I mean, eventually it's compact, so things do have to converge. But you say maybe that's only at large scales.
Yes. Okay.
I mean, if you have a small k, then you e to the minus d squared over k is going to be expanded, and it does look like d squared. Yeah, so that's the one regime. So like your straight line is kind of like that.
Yeah. So for us now, one of the main problems how to choose this for the generic group. For the Rubik's cube, we know the diameter from the human knowledge, yes, and we can just approximately choose it nearby diameter. And but if we want to make what we want to make for the generic group, we need to estimate this parameter somehow. And
yeah. I bet I'm going to look because I bet that question's been asked. If all you can do is random walk on a group, how do you estimate its diameter?
Yeah. Yes. So we are still working on this. So there are some ideas. In particular, the very strange thing which we observed, we can take this Kmax smaller than the diameter, and the machine and neural network still works. We can take it 2 times smaller than diameter, and still it works. That's very surprising. That machine learning.
That's interesting. That might be the network generalizing. Yeah.
Yes, so a kind of machine learning looks only small neighborhood of the identity, but it's able to generalize. So, for example, for Rubik cube 4x4, diameter is conjectured to be around 50, but we considered the length 30, and it works. So it's quite surprising.
Well, maybe that's exactly the remnant of conjugacy classes. The fact that you have a non-trivial structure.
Yes, maybe, but yeah. But maybe it's some generalization ability of the neural network.
Yeah, it's worth understanding.
Yeah. Okay. Any other questions or comments?
Well, one comment that is maybe relevant to some people here is that, of course, this version of the problem is close to Rodemeister graph. So in the case of knots, so we can represent vertex by each node is a planar projection of a given knot, and they're connected by edges whenever we have Rodemeister moves connecting two different diagrams. And then basically many questions in knot theory, like a knotting problem, but also many others can be essentially formulated as a pathfinder of the type that you described, Sasha. And I think it would be fun to, I don't know if anybody implemented exactly your method for the Meister graph, but I think it would be fun to do.
Yeah.
So basically take your code base and re-implement.
But how do they represent these projections? Because we work just with the permutations, just vectors, integer vectors, or matrices, integer matrices.
Right. So there are, yeah, we had this discussion on Monday how to present planar projections. They could be sequences of zeros and ones in path hole diagrams. They could be words and braid group. I mean, there are many, many different ways to represent it.
But do you think something like a fixed length? Fixed length.
Well, yeah, you have to always put bound on length, right? So, but my point is that in different, I don't know which presentation is better for this particular search augmented with a beam search, but I'm just noting that it would be fun to apply it to this Meister graph problem.
Okay.
Where you, which is, yeah, very, very, very similar. So it's not a Cayley graph, or closest would be like a Cayley graph of a braid group, but it's close cousin.
Well, it's a group action graph, right? I mean, you can generalize.
The Meister moves are not, they don't form a group. It's like a semi-group probably at best, but it's close cousin. So in that sense, it's good that it's not literally within the class that we're discussing.
Why can't they form a group? What's the objection to that?
Yeah, so our approach is not restricted to the Cayley graph, so we can consider any graph actually.
I have to think about it.
So it can be.
Yeah.
Yeah, they're not really using the group property very much. You know?
Right. Exactly. Yeah. In that sense, I think it's very good to. I mean, yeah. Thank you for advertising this big goal of trying to find long path. But I think much more concrete application would be just to. Do say unknotting problem, for example, as a simple baby exercise using your greedy plus beam search.
Yeah.
I would be curious what comes out.
Yeah. May I make a small remark also about this, if time permits? About not.
Yeah.
Okay, so there is some idea, we haven't yet checked, but it looks like this. So we take a braid group, yes, and so the knots are the braids modular Markov equivalence relations, yes? So if we take a braid group, we can compute a graph embedding, or we can take a finite factor, for example, of the braid group to make a graph finite, and then there is no problem, just compute the graph. Now, how to make the embedding, in some sense, Markov equivariant, yes? So the idea is, again, quite simple, that we can run something like a random walks by Markov relations. That means we'll connect the two embeddings if they are related by the Markov relation, and we'll have a contrastive loss. If they are not connected, just that means that choose randomly. Contrastive loss, it's you have positive examples which are connected but Markov relations, and negative which are chosen randomly. And then if we optimize a neural network, hopefully the braids which are related by the Markov relations will be concentrated in the clusters. You will see Markov equivalence as a set of clusters on this new graph embedding. And then we can just take the centers of the clusters, for example, and it will be something like a not invariant. What do you think about this idea?
Yeah, it's interesting. We heard similar things from Fabian and Jim the other day, but it seemed like a good idea.
Yeah. Yeah, so this is very close indeed to what we were discussing on Monday. So yeah, I think that's very cool.
Okay, thank you very much.
Thanks.
Okay.
Yeah, thank you, Sasha. These were good ideas, I think. Many parallels, and yeah.
Yeah, just a last remark, very short. So beam search is very simple, but actually there are many improvements which can be made. And now beam search is popular in large language models actually. And so people are working a lot. So here, well, I will not go into details, but at least there are 10 items how we can improve the beam search, and it can be quite more effective. Okay, then thank you very much. Sorry for taking your time.
It was interesting, thanks.
Yeah, thank you.
Yeah, you're welcome.
Georgi,
Yeah.
so Georgi and Fabian did a lot of work on Humphrey and related things, so I don't know.
Yeah.
Sure, but there's a lot of exciting stuff.
So essentially the idea is to predict the 4D genus of a knot, and I don't know if Fabian already discussed the types of encoding yesterday, but the one that I'm going to talk about now is the deep sets type of encoding. Essentially the idea is that you have polynomial represented as such. All you have to do is really just construct a deep set where you encode the degrees of individual variables and the coefficient in front, and this is automatically going to make it equivariant in the sense of invariant under permutations. And in this case, what I set it up with is to run it as a classifier to predict it as a 4D genus. I did try it as a regression, and I'll mention that in a couple of minutes, but one of this going to be in this notebook is basically the one that I set it up to run it as a classifier. So this is a network. Essentially, it's very simple deep sets construction, and let me show the results that I'm getting out of this. So on the validation, this is the evolution, and it gets quite high accuracy on both training and validation. In particular, it gets about 94 in this run that I just did, and 99 in training. So it seems to be matching some pattern, but the problem is that the data set is highly unbalanced in the sense that there's a lot of them which have genus 1 and very few of them which have compared to the one that they have other values. So I essentially try to run it separately, or essentially compute the accuracy for predicting individual ones, and the actual values are, let me just quickly open it here. So when on the training set, it's on the bottom, and on the validation or test set, it's basically this one, and it has highest accuracies for everything from genus 1 to genus 5, including genus 5, but it struggles with genus 0. So, and I guess that could be explained based on the fact that there's very few of them compared to, say, genus 1 or genus 2, where there's a couple thousand that it sees in the training set.
Sorry, you're going a bit too fast. So can you slow down? So
yeah. Oh, sorry. I just realized I'm not.
Right. No, we have time. But what was the split, and why is it?
Yes.
So you did something that caused genus 0 to be
yes.
performing poorly. So why? What's happening?
Yeah. So essentially, what I just did is basically the following. So I'm using the essentially betting the predictions based on the genus.
Mm-hmm.
And then just averaging in that class. So how accurate it is for predicting this class. In this case, this is split according to the genus. So how accurate it is for predicting genus 0. So I'm checking essentially all the expected values being equal to genus 0 and checking if it actually predicts. So if it's actually
right, but I'm asking about train set, because you obviously did something to train set, as we discussed before. Most of them are genus 0.
Oh, I didn't change training set. I'm just using training set as usual. I didn't split them in a different way. I'm just doing the usual train test split. There's very few of them, so it was hard to come up with a way to balance them in some way so that I get equal.
So you're training on these 13,000.
Exactly.
So all of them.
I'm training essentially on the 75% of all of them, and 25 is used for testing.
Okay,
so it doesn't see those 25%.
I see. Oh, okay, that's interesting.
And the accuracy that I was just showing are on this 25%, which it doesn't see during the training. It is overfitting in the sense that on genus 0. On the other ones, it is not overfitting. So let me just go back to this one. So for all the other values of genus, it's producing around the same accuracy in both the training and validation, meaning about 90%. And on the training set for genus 0, it uses something that it basically means that it's overfitting in genus 0 in the sense that the accuracy for on the test set for genus 0 is quite low.
So this is very interesting signal because genus 0 are precisely the ones which are called slice.
Yeah.
And that's basically the most interesting thing in a way. So it says that for high values of genus, it gets very reliable actually, but sliceness is exactly hard to detect.
I mean, it makes sense because you can use these to obstruct the sliceness, but you can't use them to prove the sliceness. You can use all of these invariants that we are training on to obstruct maybe slice, but you can't say anything about maybe.
Actually, what is it's learning from home flip, right?
Home flip, yes.
So it's very cool because from home flip, we can't really, we didn't introduce anything mathematically rigorous that obstructs it yet. So it's actually already pretty cool.
Yeah.
That's the, yes.
But I see, I hear it.
Unless it's just all over fitting.
Maybe.
Yeah. The only way to be sure is to really just extend the data. I mean, there's only 13,000 elements here because it's only up until including 13 crossings. And there's not, it's very few.
What's the highest crossing number that you have?
13.
13. And I mean,
Six. Sorry,
Yeah.
I just want to remark that I found the exact same thing in my model. So genus 0 is very, very difficult, and I have a rough conjecture for why that is. I mean, yeah, it's interesting that it's because of slice, but yesterday I shared with Sergey and Georgi sort of how the distributions are for the different genera of the coefficients. So if I can quickly show this, I can explain what I mean.
Yeah, actually, if Georgi can stop sharing for a second, maybe Fabian, can you share this graph where you had the, I mean, another thing that's common between you two guys is that some of them are dead on the nose, right? So you had a sample where 10 out of 10 were correct predictions for genus, for example. So can we see that?
Which one do you mean? Where?
So you did a sample and checking how often it correctly predicts the genus. And sometimes it was like 5 out of 10, but some of them were 10 out of 10. And I think this is very similar to what Georgi just showed us.
Let me share it. I'll share this.
It was, no, not the confusion metrics, but a much even simpler plot. Like you'll see in a second.
Oh, sorry, I thought you meant the confusion matrix.
Not the confusion metrics, but graphical representation where you had like, confusion metrics is also good, but remember you had a sample. On particular nodes, you try to ask, out of 10 tries, how often does it predict correct genus?
Yes. Yes. But so, this, yeah. This was...
it was basically sampling, but I think it was a very, very nice plot. Because suppose we want to use this as a tool to predict genus. So surprisingly, on some, just from Hopefully, it already learns how to predict it really well. And mathematically, to me, this is pretty cool.
This plot, you mean?
Oh yes, that's the one. Yeah.
So what I did here is, I can quickly explain what this plot is. So what I did here is I used bagging. So I trained 10 models to predict genus. And what you can see here is, so these are not in the data set for which the genus is not known, but the lower and upper bound is known. So for example, for this one, the bound is between 1 and 2. So here's the statement. So for this, it's known that the slice genus as the G4 is known to be between 1 and 2, and 9 out of 10 neural networks actually predicted genus 1 for this node, and the other one predicted genus 2. So you can see, so this is how this plot comes about for this point. And for some nodes like these here, all 10 neural networks, you see 10 out of 10 neural networks predict the same. But then there are some nodes where neural networks are really, really undecided. So here, 5 out of 10 predicted. I mean, so 5 out of 10 doesn't mean that the other 5 predicted something else. I mean, if you look at for example, at these nodes, you get a huge spread. You get the genus is predicted between 0 and 4 for this node, for example, and 5 predict genus 2 for this thing here.
But I think it's extremely impressive that just from Hopefully, half of this unknown, mathematically unknown guys, according to neural net, should be known, and that's the value.
Yeah. And so the majority prediction always fit into these bounds, which is also interesting.
Yeah. But I mean, the fact that there are 10 out of 10, to me, this is quite striking.
So, but you confirmed the prediction for this, not?
Well, there is no, I mean.
We just have the
Yeah.
bound, and it's within the bound.
It's a highly non-trivial mathematical theorem if someone can confirm it. So, yeah, but it's amazing.
So you have
that,
predictions that
exactly.
can go out there as conjecture.
Yeah, yesterday I was asking Fabian if you're willing to put career on the line, and I guess in this case it's probably yes.
Okay,
To
that's a
make this
serious
prediction.
prediction,
Yeah. So this is pretty cool mathematical result. Yeah. Because it's not really known, and proving this is extremely hard.
Yeah.
So you're going to say something about that?
I wanted to say something that the data that you're using up to 13 crossing,
Yeah.
most of those knots are quasi-alternating, and for these knots, signature is usually a very good predictor of this slice genus, and you can see signature from this polynomial.
Well, yes and no. So actually Fabian, he explained to me a couple of other experiments he did. In particular, in some cases, the model works really well, even when it's far from signature. So in fact, I think he tested it. I don't know if you Fabian want to comment on this. That was my concern, that on such a small training set, we're just learning signature. So,
I wanted to see if that's not the case.
That's not the case. That's actually great. So yeah, I don't know about Georgi's model. We can discuss it a bit later, maybe or now. But Fabian did check that he does not learn the signature.
Yeah. So
he learned something else, and that's good. So it's.
So if you're doing it with 13 crossing and it's not learning the signature, I guess if you go to higher knots, then it will get better, because in higher
probably.
knots,
But one question we ran into with Fabian yesterday is that, and that's of course a very obvious question, we're trying to learn very cool invariant. So to answer Mike, I mean, there are no tools we can, I mean, it will take Lisa Piccirillo to verify this.
Yeah.
So, but going higher, we'll get more and more unknowns, right? So because we have no way, it's not even an algorithmic way to compute the four-ball genus. So we're going after very delicate quantity here. So.
Yeah, and I mean, some of these polynomials are even computationally hard to compute for like a knot with 40.
Right, but polynomial at least has algorithm. I mean, we were complaining on Monday that, oh my gosh, it's very slow, it's not slow, but four-ball genus has no
There is no
algorithm.
algorithm yet.
Yeah, so that's the problem.
It isn't Humphrey as efficient. The algorithm for computing Humphrey as efficient as Jones.
It's the same as
The same model, yeah.
Yeah, same complexity. But I don't know if you know any good sources to look up G4 in, say, 15, 16, 17 crossing range. So we were talking about all kinds of software packages. Do you know anything that?
No, I mean, one thing that I know is usually people that want to impress their advisor, they pick one of these things that are not known and they try to prove it's like one or two. And that becomes their thesis. That's the way.
So Fabian just did 7 theses, 7 graded students.
Yeah.
Is there any virtue, because this model can just spit out predictions for as many knots as you want. So is there any, in your context of this genus problem, is there any value to not just knowing a prediction for one knot, but this whole set of knots related by changing one thing?
Usually only when it's some special family like alternating or two-bridge or something like that. But these are random, so this is truly random. So that's actually in some sense even better.
This becomes more interesting if you do it for, so right now you're doing it only for 4-ball, if you do it for another 4-manifold, but then your data becomes much smaller because even mathematicians don't know the genus for other 4-manifolds that much. But because 4-ball genus, in a sense, is really related to the genus function in other 4-manifolds, because some homology class is represented by that knot in a sense, and you can cap it with this because that homology class is not represented by a lower genus. Right? So, in a sense, these are also related to intersection from a 4-manifold. So your machine at the end, you need to learn like the 4-manifold and the knot itself together to predict well. Was it clear?
Well, that's much more complicated because you're turning the knot into two-handle and vertical.
No, there's no two-handle. The only thing is your knot is still in S3, but instead of B4 over S3, you have another 4-manifold here, and you want to find what genus you can put on this inside that 4-manifold.
Right, but right. So I'm not sure then what the proposal is, because here everything comes from training on some data, and the question I was asking is that we don't have much data.
Yeah, that's the issue. I mean,
Right.
there are like many theoretical ways for finding range of this in terms of the four manifold and the polynomials that we have.
Yes.
They don't give you exact numbers, they give you either one or two. And
Right.
These things are like very intertwined. So training on such a thing would give better result maybe even for just P4, predicting the P4.
Oh, I see what you're saying. So you're saying that there is, right, but I'm not sure. Okay, maybe that's useful, but that will be a lot of data. Just like here, we see a range from 1 to 2 or something, and then you're saying that providing these ranges in high number of crossings may be feasible.
Yeah.
Okay, I understand.
Is there any transformation you can make on a knot that preserves the genus? Or
You mean the slice genus?
Yeah.
Just connect some with the slice.
well, even does that change this polynomial?
That changes the polynomial, yes.
Because then you can augment the data, you can start generating.
That's actually a good idea.
Yeah, I mean even better than connect some band some with a slice now.
That's right. That's a great idea. That's a great.
That's
idea.
that's a very that's a interesting.
That indeed will help to.
And even for like generating, so if we don't have enough slice nuts in the data set, you can also just generate random slice nuts by picking an onlink and adding a bunch of bands just randomly.
Right. That's exactly what we're doing. That ribbon finder, but in reverse. So.
But I'm not sure if computing the invariance, like polynomial invariance for these nuts.
No, let's assume that okay, that's a separate problem. In some sense, because it doesn't have to be done in real time. So we can generate the data set. Our goal is to produce large data set. So what Mike suggests is actually a great idea, because we can go from 13,000 to, I don't know, maybe 500,000. And then we can run computation of invariance separately. That's done.
Yeah,
and then
that's a really good idea for getting better data set.
Yeah, no, that's great. I think that's fantastic.
Can you repeat I didn't catch it, Mike. Can you repeat it?
So just if there are known transformations that preserve the genus of a knot, and apparently there are, you can
Yes.
with some things, you can get some with this. So you can augment the data set, you can generate lots more knots with them.
Right.
Yeah, what we're studying basically genus is detection of structure in the concordance group, which of course we don't know. But an obvious thing indeed is band sum is anything slice.
Yes, yes.
So it's going to give completely different knot, so different invariance, and this can boost our data set from, I don't know, 10,000 to 50,000 easily.
Yeah.
Is it efficiently computable, the band sum?
Huh?
A band sum, is it efficiently computable?
What do you mean?
That's what I was mentioning. In our other project with FibeMG and Cyprian, we did that in reverse. So in fact, we do have, I'm not sure if that implementation is ideal, but anyway, this can be done. So yeah. Right. And then maybe Fabian and I will have fun coding some other environment just for balance, to do something different from.
Yeah, I mean, we can construct infinitely many genus zero sums. So what genus zero?
Well, but we have the band sum constructor. So I think
exactly. So you can just sum this with any knot of known genus to produce a new knot of that genus. Yeah.
Exactly. And that's the suggestion. So we can take lots of slice things that we already know. In fact, we can even get slice of very high crossing number. Right?
Exactly. Yeah.
Because now we have a tool to produce like generic slice things. So I think that's a great idea. We can easily be in large number of crossing territory with this.
Yeah.
So
I mean, they could be special in the sense that most of it is sort of genus zero, and then we put something like a 13 crossing knot where we know it's genus 1 in there or somewhere else. So
well, genus 0 has to be the case because we were trying to have guarantee, right?
Yeah.
So
what I mean is. Well, I mean,
that's fine, because genus 0 guy is going to be super complicated. It could be 30 crossing, right?
Yes.
So we take lots of those. Yes, it's true that, I mean, to me, the bottleneck is that we are, as a seed, we're using this 13,000 database.
Yes, exactly. That's what.
That to me is more of an issue.
So if let's say we want to create a knot with genus 1 or so with 100 crossings. So we can take something that has 13 crossings and it's genus 1. and add something that has 100 crossings to this genus 0.
Yes,
But then
exactly.
sort of, there will be sort of this small genus 1 part inside this huge genus 0 part.
Exactly.
So that's the sample bias.
Right.
That is zero.
Yeah, so we'll definitely create, yes, this sample bias.
But if you make your band complicated, I mean, if you add a simple band, yeah, you basically have a bias instance. But if you add a very complicated band,
right. So I totally agree. So in that sense, yeah, as we did, many of us discussed in different like subgroups and discussions, having complicated band is somewhat compensating for having complicated node.
Yeah.
So in that sense, I am not too worried about sample bias in this way, but I think we will have sample bias of very low genus because we're starting with this 13,000. The genus never goes to more than 7, right? As your histograms show.
Yeah.
But in 40 crossing nodes,
but you can also make sure your genus goes up by bounding your signature from below if you pick. So many of these 13 crossings not for these the signature detects this slice genus completely. So this genus is equal to the signature.
That's right. So okay, that's very smart.
So you can add up with the signature to make it high enough, and then.
Right. So the suggestion to spell it out was that we can play this game not only with slice nodes, but with nodes which satisfy the bound. And when we have control.
With nodes where the slice genus is very close to signature.
Exactly. So okay, that's gonna get us like a huge data set. Okay, these are all great ideas. This is fantastic.
I need to leave soon, so I wanted to say one more thing with the genus 0 versus genus 1 problem, and then I need to leave.
Actually, some of us also have to leave here. Okay.
Okay. So this is the confusion matrix for simple neural network I trained. So I mean, this can be improved. This has 91% accuracy or so. So you see, in this case, it's predicting 0% correct with genus 0 from the test set. But genus 1 is the majority. So
wait a second. Does it ever predict a 0?
In this particular case, it doesn't. I mean, I've had cases where it did, but in this case, it didn't. But so what my point is, so now I plotted. Let me go to this. So I did a gradient saliency analysis to see sort of what it uses, what type of coefficient it uses to detect what the genus is in its classification, and I get pictures like this where. Sorry, let's look at which one do I want to show you? Yeah, so I roughly get pictures like this where it detects sort of for genus 0. So this is essentially a superposition of all the genus of the saliency analysis if I only feed it genus 0 nodes. Everything that lights up to detect genus 0, everything that lights up to detect genus 1, everything that lights up to detect genus 2, and so on. And then I looked at the distribution of entries for genus 0. So you see sort of for genus 0, these Humphrey coefficients are non-zero here. And this is for genus 1. So you see sort of genus 0 and genus 1, they look very, very similar. We always get these diamonds, except that sort of genus 1 spreads out a little bit more. So now if I look in the saliency analysis, what it does to detect genus 0,
but actually, maybe given what you and Georgi say, it's actually easier to start with high genus because it detects high genus really well. So maybe there is much simpler structure there.
Yeah. So yeah, exactly. So let me try to explain. Yeah. So
you have some nice splitting in the coefficients.
What it does here is it mostly looks at these two. So it doesn't even look at the center here, as you see.
Mm-hmm.
But the center is precisely where all the data is sitting in some sense.
Right.
So to make its decision here, it's checking. I think it's checking on the outside of where the thing is sitting. So if it was to find something outside, it would know it cannot be genus 0. So I think in this case, it's making its prediction by checking sort of around genus 0 to see if something is there. And if something is there, then it would be sort of one of the higher genus ones.
Mm-hmm.
So that's why it's lighting up these. And so if you see for genus 0 and genus 1, this looks very similar. And of course, you can just check this hypothesis by doing something like an adversarial attack where you take we add some noise when you turn a donkey into a hand grenade or something. So we could add this coefficient here and then see that it all of a sudden will predict genus 1 or something. I mean, this would be a not, but sort of to just check this hypothesis. And you see that, yeah, sort of what is happening is for the higher genuses, this diamond splits and then it wanders off in two different directions. And this is just a single sample, so don't read anything into this genus 6 thing. But so yeah, so by checking individual points in here, I think it can determine whether or not it can possibly be this genus, and then it checks other ones to rule out that it's not another genus. I think this is what it's doing.
To some extent, this makes some sense because, for example, later we may discuss this Higard-Floyd thing, and there the maximal powers determine the cipher genus, basically. So it's actually a good idea to try to ask what is the spread, what's the span of it, because that determines at least close cousin of the four-fold genus.
Yeah. So all I wanted to say here is that essentially genus 0 and genus 1, the data looks very sort of the distribution of coefficients in front of in a Humphrey polynomial. They look very, very similar, and the other ones sort of look different. So it's more difficult to distinguish these two than, let's say, any of these from the other ones. And maybe it performs well at high genuses because of these diamonds split and move apart. And then sort of it's easier to just sort of probe the pixels here and distinguish and sort of say which higher genus it is if this moves apart. But for genus 0 and genus 1, it's essentially the signal is sitting in the same region more or less. It's just a little bit more spread out genus 1. But in this sense, the genus 0 is contained inside the genus 1 region, so it makes sense that these are harder to distinguish.
I'm getting similar split when I do the saliency analysis. So in my case, the splitting is even more apparent on the neural network coefficients because mine is not a matrix now, so it's just looking at the inputs themselves. And there I see this.
This is not. I mean, this has nothing to do with the neural network. This is just the distribution.
No. I'm saying the saliency analysis when I do on the neural network produce similar pictures. So
you mean these ones?
Yeah, something like this, but only using the deep sets. So I'm getting something where the picture that I'm getting using the saliency analysis looks similar to the pictures or the distributions that you're getting for the coefficients, which kind of makes sense because it's sort of like if you were to treat it as images, it's sort of like checking if there's an object there. Or
yes, exactly. But I think sort of this is mostly checking whether an object is not there in this particular case.
I'm getting something slightly different using.
But something that should be similar for you guys is IJ, right? So the meaning of IJ is the same in both cases.
Except in my case, it's A and Z, and here is Q and A. But
well, I also did AZ. AZ is
it was my request to do A and Q because some of the spectral sequences and homological things are easier in Q than Z.
So AZ is this picture, but then sort of it's more or less you can just take this and flip it upside down to complete the diamond. So you see this is the bottom half. What you're seeing here is essentially the bottom half of this diamond, more or less. I mean, so all I did is I replaced Z by Q minus Q inverse.
How did you compute the salience for genus 0 when none of them are predicted as genus 0? Or is it overall data set?
So this is the saliency map for
test? Or
what I did here is I just took all genus 0, so all 511 exams of genus 0.
So that's also from train set, right? That's
exactly, that's from the entire data set. But I mean, the thing is not overtraining. It has 95 to 94 or so, or 9 prediction accuracy. So it's not it's the same on train and test. But yeah, of course, ideally I would like to test with something else, but we don't have enough data. So I'm just taking all 500 examples of genus 0. I pump it all through the network. I record all the gradients. I superimpose them, and I draw the heat map. This is how I got this. And then the same for all the other genera.
Yeah, to try for both subsets, like test just using test and train. And I think the figures that I'm getting are mostly similar. So I would suppose that probably it's going to be the same case in your architecture, but the figures are probably going to be similar.
Fabian, but maybe I missed it. So Georgi was saying that so he in the beginning he sliced his train val. No, train was everything, but val set was split into performance on different genus. So do you have that or not?
No, I just took 90% train, 10% test, completely randomly selected.
Right. So I think his concern might be that most of the failures could be there indeed in genus 0. Then we should trust the genus 0 saliency map less.
Yeah, I 100% agree with that because yeah, as I said, so for this particular case, it didn't get a single prediction right for genus 0.
The splitting there is essentially the same thing as the confusion matrix, but now I'm averaging so that I can do.
Yeah, exactly. Okay, good.
I mean, I can improve this if I trained this more and sort of did hyperparameter tuning. I just took a simple run, which took 8 seconds or something to run. So this is not it's not a very deep thing.
So we have a couple of minutes. So maybe you want to share again. You said that you have something slightly different.
Yeah, I'll just quickly share. It's essentially the same saliency analysis, but actually these are the figures that I'm getting for salience for genus 2, for example. And as I reach genus 3, and there is this splitting at so this is on the test set and on the whole data set, because in the test set there's much fewer, I get something like this, which is similar to the pictures here, which in the sense of the splitting into two different branches. So let me just open the.
And also the corner kind of this red guy lights up a lot,
Yeah,
right?
exactly.
So it's looking for is there far spread or a large span?
Exactly. That's similar to, I think, what you, Fabian, were getting in the sense of there's one coefficient that was lighting up, which was contributing most to the decision of the neural network to produce a certain class. And I'm getting most similar numbers that you're getting, I think.
Yeah, we should look at the powers and try to interpret it mathematically.
Yes. Yeah, that's the next step, but I didn't have time yet to think about it.
Yeah, that's essentially it.
Yeah, this is super exciting. Genus was completely inaccessible until this week. All right, so maybe we should stop here.